meet all check and carry on linkage is subject to search.
Hi, Harry. Hello.
Hello.
Everyone. Thanks for joining. I suppose we'll give it a couple minutes just to make sure everybody's in the meeting before we start.
Right.
Yeah. Do we have Mike on the call? Is Mike ready? Mike Ranieri.
Yep, I'm here. I'm ready.
Yeah. Thanks. Hey, Mike.
I didn't know if there were other mics on the call.
Yeah, understood.
And Steve, this is John Leung. I'll be starting off with a couple of slides before handing it off to Mike.
Oh, okay. Yeah, that's absolutely fine. We'll just wait one more minute and then we'll get started, guys. Yep, there we go. So yeah, if you wanted to go first then, John, you want to share your screen, we can just check if it's showing properly.
Okay, does everyone see this slide?
Yes, we can. Yeah, if you could put it in present mode, that would help as well. Yeah.
Okay.
Perfect.
So I'm just going to give a couple of slides before Mike takes over to understand what we're trying to do. Mike basically has a proposal for manageability of a power shelf, and he'll be going over the usage guide. And I want everyone to understand what the relationship between that and the actual profile is. So the way we do OCP projects is that there's a center of excellence, I guess, for our hardware management, which exists in the hardware management project. There's a baseline profile that we release, which is the common manageability across all OCP platforms. However, there are and other projects are expected to extend this baseline to manage whatever they need. There are server projects which has extended the baseline. So with so what we found is that most of the SMEs for servers, for racks, for networks are all in other projects, and so prescribing of manageability for these entities should be done within that group. Now we have profiles which are machine readable. I have a specific, pardon, which have a specific syntax and semantic, and we don't want the SMEs to have to
So
learn.
it would have to be something that we could wrap like at this point.
Excuse me, someone you need to mute. Mark
barrier. A lot of times you can leave it open and they can seal it once the part.
Sorry, guys.
Oh, so
No problem.
I don't have a way of kicking in. Mark SR, can you please mute?
Like
okay. So you're saying it'll be like a big
the
piece.
whole thing would be
Excuse me, Mark SR, could you please mute?
Okay. Right.
open the crate. See this? You see it boil down.
Sorry, guys, I don't have a way of muting in. Harry, do you know if there's a way?
So, but the foil bag would be on the bottom, and then we would build on top, and then, or would it be a bag, or would it be?
Harry, do you know if there's a way to?
No, I'm just trying to look exactly. I'm just trying to do the same thing. I wish there was. This should have been, or we should look for that control in the future to stop these disruptions, right?
Yeah, definitely. Mark
boy.
Senior, it might be Senior. Mark Senior, can you hear us? Hello, Mark.
Yeah, that's it.
Sorry, guys.
Okay.
Sorry, yeah.
Mark Senior, can you hear us?
Okay.
He cannot hear us.
You know, we can send a note after the meeting, and I think we should get going in the interest of time. And I
Yeah.
apologize for this.
Okay.
Yeah, sorry, John. If you could.
Okay,
try
I'll try to speak
Like
loud.
this stuff right here.
Shit. Okay, I'll just place on, guys.
So,
Okay.
So what we have is that we don't want SMEs to have to learn about this syntax. So we've created a revised process to allow the SMEs to provide feedback and input without having burdening them with understanding any of the syntax. So that's the notion of the usage guide, which is what
What's the vapor?
Mike will be going over.
The vapor is a liquid.
So, so the relationship between the usage
It's a
guide and the
gas version
profile
of the liquid.
is that the usage guide is has a requirement of what type of tasks need to be done to manage a particular entity, and it requires this knowledge of what the mockups are, and they are approved by the project. So we would like your input, and if you actually want to approve the entire document, as this is all the manageability that you guys are interested in, we can do that. And this is the document which actually goes up to the steering committee to get approved as a new profile. Once that's approved, the work can be done to actually generate the JSON file, which is associated with that. So the JSON file is needed because there's actually a auto validator which will read the JSON file and auto generate the test and use that to test a conformant implementation. And that's all required in order to get OCP accepted and OCP inspired. And you guys actually make that requirement. You guys can say you just have to manage the baseline, or you can we've created a new profile and you should adhere to this profile if you are a PowerShell. Any questions? So so again, the focus is on the usage guide. That's what Mike will focus on, and the profile just gets done automatically.
Like this, but they're reversed.
Okay. So the usage guide, this is just a general structure. The general structure just tells you what the interaction is. It has a list of all these use cases or tasks, and it says, you know, in order to, and each one has a reference to exactly what the interaction is. So Redfish is RESTful, so it tells you exactly what the action is that you, the command that you issue, the response that you get back for to complete the for getting the status of the chassis. In this case, this is the fragment that. In this case, this is the fragment that gets returned. And so at the top of the document, basically there's a linkage between the user's guide and the profile itself. And it tells you exactly where the profile is, which is on a GitHub repository. So people can download the profile and run the validator against it. Any questions? Later on, what we've done is if we're now doing the document in a Markdown, and that's what Mike will be doing his discussion in. We have the capability of converting that Markdown into a PDF or HTML file once the all the edits are done with the Markdown file. Any questions? Okay. Mike, it's all yours.
Excellent. Thank you, John. You'll need to stop sharing so I can take over.
Okay.
All right. So what I'm about to share is it's a pull request into the OCP's hardware management profiles repository. So this is where we've been keeping track of all of our profile work. I'm specifically focused on a rendered view of the management specifications, just to be able to talk through the different use cases that I've outlined and hopefully get feedback on if this is the right direction to go or not. As John already indicated, there's the baseline expectation that everything stems from a baseline profile that's already covered in the hardware baseline management specification. So this PowerShell Management 1.0 specification is an extension of that baseline specification. And as noted here, the profile syntax will reference that to build additional requirements on top of that. Going through the capabilities, which is really each of the use cases to outline. There are many that are already covered in the baseline management specification, which I won't go through in detail, but you'll have things like being able to manage your user accounts, being able to manage your active Redfish sessions, getting hardware inventory of the box, being able to get and set your indication LED, getting your overall chassis status, getting power metrics, temperature information, cooling information, event logs, and anything about the management controller in terms of what its firmware information is, its network settings, being able to reset the controller. There are additions that are being proposed to build more extensions to the baseline management spec to cover other types of tasks like firmware update, but that's currently not in here right now. Specifically for PowerShell, so this is where we start describing PowerShell specific use cases. These are the use cases I've built out based on the types of information that's available in the Redfish model for a PowerShell. So threw it into a few different categories. So from a power perspective, being able to get the power supply information for the power supplies in your PowerShell, being able to determine your power supply redundancy, to get your metrics on each of the power supplies, get and set your individual LEDs for the power supplies, and get your overall power consumption. Getting your PowerShell's internal temperature. Then there's optional cooling requirements. So if your power supply has internal cooling capabilities, maybe there are fans installed, being able to surface that information if that's implemented. And then strictly with more of the functional aspects of the PowerShell, being able to get the information about the PowerShell itself, its own metrics, get all the main and branch circuit information, and if your PowerShell has discrete outlets for certain smaller use cases, being able to get the outlets that are on the PowerShell itself. I guess before I jump into the details of these use cases, does anyone have any questions or comments about what's outlined so far?
So one of the things we want is feedback on whether this is a good set of tasks that need to be done against a PowerShell, whether we're missing something that most people commonly do and are not in here. We do not want to be limited by the Redfish model, because if it doesn't exist in the Redfish model, we'll add it to the Redfish model in order to complete a task. But we want it basically driven from the task that something has to be accomplished, and therefore the Redfish model can alter itself to or extend itself to meet whatever that task need is.
Yeah, that's usually a good way to get feedback into DMTF for extending the Redfish model, is that you know, as a consumer and implementer of a Redfish interface, you may say, hey, I have a set of users or use cases that I think are very common, and I want to make sure that the standard has those, and it doesn't seem like that's true. So having that feedback is very important, and we can turn that around in just a couple of months within DMTF.
And so that's the one thing is the list of tasks. The other is the requirements. So, you know, I have a feedback about this get set power supply LED being mandatory. That if you don't, if not every power supply has an LED, you know, should we change that requirement to be less onerous, everyone? Because the goal is that anyone who builds a PowerShell, right, be able to run and has a management interface, be able to run this profile and be able to pass all this, all these requirements.
Yeah, that's true. I come from a world where every power supply has an indicator LED, and so it's if folks have products that don't have an indicator LED, we don't want to put that in the profile if that's if that would mean you would not pass conformance just because of you don't have a blinky light.
So so Mike will go through the rest of the document, which is actually looking at the use cases. I think that's less important than this table right here. If we don't get this table right, then someone will come, well, why do you make the LED mandatory? My power shelf won't pass it, and I can't put it in the OCP marketplace as inspired or desired because of that. So that feedback is good. I like to make this a a a threshold that most people can pass, as opposed to making it so onerous that that particular power shelves cannot pass.
I think it's also important to note that as this is not a final list for forever, this is certainly the 1.0 version, and there will be a 1.1 iteration that builds on this capability. So adding new features that become mandatory in power shelves over time. I think at least getting a very bare bones baseline 1.0 would be very useful as a building block. So I'll pause for a moment if there's any comments or questions or any early feedback about this list of use cases here. Okay, sounds like there's no feedback right now, which is fine. I'll make a I will make a kind of either an HTML or PDF copy of this page, just so folks can have something that they can pass around internally and solicit feedback, so that way I can incorporate it into the spec and ultimately the profile in the end.
Mike, hi, this is Harry. I think this makes perfect sense, having a broader view of all the things one needs to control and one needs to get hold of. So we will need to work with, not only the vendors, get a consensus here, and plus our, customers as well, so that, we can agree on this so we can make it sort of a standard. I think it's a good approach.
Yep, sounds good. All right, yeah, so again, I'll pass this around, so because I know not everyone is comfortable with using GitHub as a way to review and request changes, but I'll have a hardened file of this, so that way we can post it somewhere and get feedback that way. Yeah, for reference, I do have some diagrams in here that show the redfish modeling pattern for power shelves. There is a functional view which leverages the power distribution unit model within redfish, where you have a power shelf collection within power equipment, and from there you can discover your individual power shelves, get further information about the power shelf, get your metrics for the power shelf. Then you have your mains, branches, and outlets collections to get information about those subcomponents. And then from the physical view, which is based off the redfish chassis model, you have a chassis collection. Likely in a standalone power shelf unit, you would just have a member of one for the power shelf itself. You have environment metrics. You have your thermal subsystem if there's thermal information and fans that you need to report. You have your power subsystem, which is where you'll find all your power supply information. And then you have a sensors collection for all of your raw sensor readings that you may want to surface in the product. All right, so looking at each of the use cases for what to expect in those payloads, get the power supply information. So this shows a sample response of getting one power supply. So redfish 1 chassis power shelf, power subsystem power supply is 1, and then this last identifier is going to be different based on what power supply you're trying to target within that power shelf. Then you have your status indicator, you have a line input, your through information, your indicator LED, its capacity, allowable inputs, its efficiency ratings, any output rail information, and location within power shelf. So being able to line things up with a service label for a user to go up into to a box and see, oh, here's the label of this power supply, so I know if I need to replace it, I go look for this little sticker on the box.
Mike, I don't think we need to go much beyond this, right? Because the structure is well understood, right? We issue a command, the command path is kind of described by the diagram of exactly how you wander down this path. And then once you issue it, you get a response back, and this is
Sure.
the content of your message.
Yeah. Okay. I'll try to speed through the others since it can be an eyesore
Yeah.
for folks who are not accustomed to looking at redfish.
Right. So I think going through the rest of this isn't particularly useful for us.
Well, I guess well that's really all the meat of the document here is really outlining these use cases and mapping them up to the different types of URI requests that a user would make.
What I will mention, if you show one of the examples, is that the profile syntax has the ability to say which one of these properties actually need to exist in the return. So I think he's listed maybe more than necessary. You might have a different opinion.
Yeah,
but
I do show a more complete view of the resource rather than what is mandatory in the profile.
Right. So what I found is you should show the ones that are mandatory and then reference them to the schema guide to say, hey, there's a whole bunch of other stuff that I haven't showed here because I want you to focus on what task you want to do, what you issue, and what you got back, and your task is complete. Redfish may return all the additional stuff, but in your code, client code, you can ignore all that, right? You're searching for one set of properties.
So John, do you think it would be worth pruning this document a bit more to be in line with what's in the profile?
Yes.
Okay. Can certainly do that.
And then I usually put a reference to the schema schema document as a specification to say, hey, if you want to know the rest of the stuff you'll get, and you'll probably may or may not wish to ignore, you can go look at this document because you'll show everything.
Okay, no, that's fair enough. I can I'll prune this down quite a bit so that way it's only showing the mandatory, at least things that are called out in the profile.
Right.
Okay. Any other questions or comments? Anything folks want to see in particular that I could help out with while I'm on the call? All right.
I think we will take it back, Mike, and circulate this, like as you mentioned, try to get feedback and see perhaps this could be, enable PMC, right, which is a power management controller, and we try to get that going, and these could become certain commands there or whatever, right? But I think this is a good start. Thank you.
All right, thanks. Is there a place I should put a PDF or an HTML file that would be best for everyone?
You can send it to Stephen and I, and then we can circulate that.
Okay, excellent. Thank you.
Sure.
Thanks, guys. Thanks for your presentation.
All right. Thanks for your time.
Thank you.
All right. So we're moving to the second part, and we don't have anything particular on this agenda, but definitely we would like to hear of feedback on the things that people would want to see in this. I was particularly interested in, there's an interest on power, higher power that is. I want to hear from the community as, we have seen 5.5 kilowatt is, what are the views? Do people want to see different variants of shelf or anything else? Somebody wants to comment, so I'll just pause there.
Well, this is Joe Urban from Oracle. I mean, we're certainly looking forward to higher power shelves and looking at what we can do at the whip level and bringing high power to the racks. 5.5 is a pretty reasonable stopping point because that gets you to about 30 kilowatts per shelf, and so that seems like a pretty good stopping point. I can't think of any reason why we would want to have a different size for the next step.
So Joseph, are you okay with the shelf with the two whips there are, or you want to see different variants, or you're quite satisfied the way things are, I guess, in terms of bringing AC there and DC out and all that stuff?
So, I mean, one of the challenges is that the power shelf design in ORV3 is largely, has its genesis with Meta and the way that they do power distribution, which does not involve redundant AC, at least in as much as I understand it. And so, what we've been looking at power shelf designs internally that would use, power supplies that have the ability to receive AC from two whips, so with an ATS inside the supply. So it's quite different from the standard ORV3 thing, but now it allows us to have redundant AC with a single shelf. So that would be something that I would think might have broad appeal, but I haven't seen really discussed or promoted within OCP.
Joseph, I'm glad you brought this up, and that's exactly what we are looking up to the community to, people come up and talk about, propose a specification or do something, right? Because Meta did propose those specifications based on applications, and, definitely it doesn't stop everybody else to, what we have in mind. So I think that perhaps we could take this offline and see if you're interested in working on a different variation of a spec or something of that nature, which others might be interested in. And, we can talk about that later.
Okay. I did send you an email on another topic. I don't know if you I just sent it yesterday, so you might not have seen it.
Sure.
But there's another topic related to high power racks that I was hoping to bring up.
Please go ahead if you want to share that with the community. I haven't had a chance. I apologize.
Okay, so in looking at the example designs from ORV3, and in some cases you have to read between the lines and go back and read ORV2 and try to understand the legacy and trajectory of how we got to where we are. And in addition, going back through YouTube and watching lots of presentations to try and glean information that's not in any specs. And one of the things that came out of that effort on my part is an understanding of the grounding methodology being used in the racks. And there's two versions of ORV3 described in the ORV3 base spec. I'm at least aware that other cloud providers are kind of making their own derivative racks that are at least borrowing ideas from ORV3. I don't purport or suspect that they're employing the same grounding strategy, but the strategy that I watched in one presentation from Meta from I think 2 years ago was that they were using sort of what I would call a common grounding strategy, where the chassis ground bus bars that carry the safety ground from the power shelf up the back of the rack is being bonded to the 48-volt return within each piece of ITE, and creating really one ground instead of separate returns. The 48-volt return and the chassis being separate, they're being bonded together in each server. And so, thinking about that, and especially as we're looking to doing very high power racks, that practice it basically is wiring a number of different potential current paths in parallel. And so, energy or current leaving a server on, I'll just generically call it return, can split, in go one of three ways. It can either go down the return bus bar, it can go down the chassis ground bus bars, because return is being connected to chassis within the ITE, apparently. And it can also couple from the chassis out onto the rack steel and just conduct up and down the rack on the rack steel. And so the interesting part of this situation is that because the bonding of chassis ground and 48-volt return is not done in the power shelf, then any current that would choose a path on some of these, the rack steel or the chassis ground bus bars, has to find its way back onto the 48-volt return, and it's it's conceivably a pretty large amount of current, because I think as you populate the rack, you know, you could have a lot of current flowing in these alternate sources, alternate paths. And it seems to me that the server that's closest to the power shelf is going to be the nexus where that current is going to find its way back from the chassis bus bars and the rack steel back onto the 48 volt return. And if that's the case, then, you know, for example, the chassis ground bus bars and the bus bar assembly, those are fairly thick, the ones that these samples that I have, and they look capable of carrying quite a lot of current. But if that current is flowing back through that last server, then the chassis ground contacts on the bar clip for that server, I think, could be handily overwhelmed and overcurrented, just conducting these stray currents back to the 48 volt return bus bar. And, you know, there's other things. I mean, I can show you. I don't have a set of slides, but I've been working on a document to try and collect my thoughts. You know, I can put some pictures to this to kind of show you what I'm talking about. But if I can share my screen, I'll show you what I'm talking about.
Sure.
So, you know, this is a rack, and you know, I'm showing a rack with 3 servers, and I'm modeling the return current from each server as a current source within the box. And, you know, per what I've seen from presentations from Meta, you know, if you're bonding the chassis to the return line, then that return current can go, you know, like I said, in one of 3 ways. It can either go into the steel, down through the steel of the rack. It can go out the return bus bar, which is where we would most want it to go, but it also can get onto the chassis and down the ground contacts.
Joseph, sorry to interrupt. I've got a black screen. I don't know if Harry, have you got the same, or can you see what Joseph's sharing?
No, we can see it. We can see it.
Okay, it must be my connection. Ignore me. Sorry.
Okay, sorry. Anyway, so you know, it's really we're doing experiments now to try and understand, you know, where do the currents go and what magnitude are they? But the key thing is, you know, if I look at this resistor ladder that I've modeled here in this picture, and this is not a perfect model by any means, but it's just showing, like, you know, I've got a current being injected into these 3 paths at each OU in the rack. And so the current, you know, through the resistors at this level, you know, is lower than the current at this level because I've injected current from another server. But like the noteworthy thing here is that per the ORV3 spec, the power shelf does not make a connection from chassis to return. So that means any current that's flowing in the rack steel or the ground bus bar, as it comes down the rack, it has to get onto the return bus bar at this server, because south of this server, there's no path. And so, you know, whatever the sum of the current that's been injected onto the ground bus bars, that's going to have to go through these bar clip connectors here to get onto the chassis, through this path, and back out onto the return to complete the circuit. Similarly, any current that's on the rack steel is going to have to come through the shelf of this last server onto its chassis, through backwards through this the bonding wire onto the return, and complete the circuit that way. And you know, if all of these currents were for some reason nicely distributed, and a little bit here and a little bit there, then I don't think it would be much of a concern. But I have no reason to believe that that would be the case. I believe that, you know, if I have a bunch of identical servers, what I'm going to see is that, you know, at each of these, this junction here, the current's going to go that way, or that way. Actually, sorry, is it this way, or that way? And I think that the relative impedances are going to look similar at each server, at each junction, and each server as I go down the rack. The relative impedances of the 3 paths. The absolute resistance obviously changes as you go up and down, but these 3 relative to each other, I think, are going to look pretty similar from server to server. So, you know, you might expect X% to go onto the bar clip, the the ground contacts here, and I would see this server's the same percentage probably is going here. And so, the current's getting higher and higher and higher as you get on the rack until you get to the last server, and then it all has to come backwards through to get back onto the return. It seems to me. So we're just starting to collect some data. But for example, one experiment we did, we put a power supply sitting in the bottom of the rack, connected to the bus bar, and I had two servers in the rack, like one here and one up at the top. I'm sorry. What I have up here is actually an electronic load. So it's not a real server, it's an electronic load. And so it's taking power from the bar clip through the electronic load, but it's doing this with the return. So the return is coupled to chassis, and so the return current can either go wherever it wants to go on the bar clip and go into the steel. And it's very preliminary data, but it's just interesting. It's like if in the first experiment we did, this server, the load was shut off on the top server, and on this server, and this one wasn't present, but on this server, I had a 20 amp load, and of that 20 amp load, 15 amps went into the return bus bar. 25% of the current took an alternate path, and it appeared to go into the rack steel, and then up to the top server, which was mated. The shelf was mated. The load was shut off, so there was no current being injected here. But 5 of that 20 amps went up through this path and then onto the return and down. And so it's looking at this and just thinking, like, we're pushing forward to try and make racks that are going to have return currents on the order of like 1,000 amps, 1,200 amps, 1,500 amps, 1,800 amps. And I haven't seen anybody look at this. I haven't seen anybody talk about it. When I was out at the OCP Summit and I went around to the different booths and I said, hey, is anybody like looking at this? Because this seems like it could be a problem. Because if we have, a place in the rack where current forms a nexus, like I've, postulated that it might happen here, or through this bonding wire, if there's a huge amount of current coming down through the rack, that's going to maybe cause some problems. So that's my idea. And all of this, I think, is the result of this unified grounding strategy where we're bonding return to chassis, which is, it's a great idea in the sense that it'll let you use non-isolated DC to DC conversion coming in off the bus bars. You have one ground, so the logic ground of the motherboard and the chassis ground and the 48-volt return, it's all one ground. It's not awesome in every way. I mean, there are other problems, but this problem that I've outlined here in particular is keeping me up at night, and so I wanted to bring it to this forum and see, like, what do people think?
Does your diagram need a bonding wire in your power shelf?
Well, there isn't one. The ORV3 spec specifically states there shall not be a bonding wire in the power shelf. And oh, by the way, we spoke through our contacts with our, the power suppliers that we normally use, some of whom are participants in OCP. We said, hey, why is that line in the spec? And what we were told is, we worked on a 48-volt distribution in a similar system. I think it was an Open 19 system. And we found out that a huge amount of current was coming through the chassis steel and getting through our bonding wire back to the return bus bar, and it melted all the insulation off the bonding wire. And so we said, well, we don't want to do that then because that's a problem. So apparently,
so you have no way of getting your blue and your orange path back into the power shelf.
Not through the shelf. It has to go through
something else to get back to the bus bar.
That's the point, right? And as you pile stuff up in the rack, and you just have all these currents that every time there's a branch point where the current can go one way up 3 ways, it's going to split based on the relative resistances of those 3 paths.
So your arrows and your blue and orange at the bottom are kind of probably in the wrong direction then.
Right. I mean, what I was doing in this is I was doing this like back when I was in college.
Yep.
And you define the currents, and then you do the math and figure out which of these are positive and which of these are negative.
Yep.
And so that's kind of where I was at, and I was, I was in the process of, I can't remember if I did that. Yeah, I was starting to do the math and figure out what the equations look like, and it's not as simple as what I've shown here, right? Because each of these resistances, like this is a resistance of a 10U section of return bus bar, say the green one, right? It's a super small resistance, and I'm showing other things here as not resistances, right? Like, oh, these have zero resistance, but these have actual resistance. Well, we know that that's not correct. So the reality is not as simple as what I'm modeling here, but I think the general observation and the general concern is still valid, which is as current is sharing these alternate paths down the rack, we don't know where it goes to get back to the return. We know it's not through the power shelf, and I believe it's going to be through the server closest to the power shelf, where there could be some fairly high currents flowing. Now, one of the things that I've learned is that, at least on the one vendor that I talked to for the bar clip, the ground contacts are not the same composition as the 48 volt and return contacts. These are some copper alloy and silver plated, and these are just sort of stainless steel so that they mate nicely to the chassis. And so the resistivity of this path is like maybe 100 times higher than the resistivity here. And so we did an experiment to see, okay, well, how much current would seem to choose this path through the bar clip ground contacts, and it was about 2%. But it's like, okay, those contacts are only rated for like 25 amps continuous or something like that, 64 amps for 2 minutes. If I get 1,200 amps of return current, and 2% of each server's return current is going into that bus bar, by the time I get to the bottom of the rack, I could still, I think, overwhelm the current rating of those pins. And what I've seen most recently is that the steel is actually a better path. Steel has like 10x the resistivity of the copper in the bus bar, but the cross-sectional area of the steel in the rack is gigantic. Once you bond to the chassis, and the chassis mates to the shelves, and the shelves to the rack, and now you're conducting through the whole rack, that seems to be a pretty effective path. And so that current, instead of going through here, is going to have to go through the bonding strap on, I think, this last server. And there's no documentation, no literature, no analysis that would suggest, hey, we need to pay attention to that. We need to be concerned that if I'm building a 60 or 90,000 watt rack, that bonding strap on that server, not this one, but this one, might need to handle, hundreds of amps. Anyway, the analysis is we're just getting started taking real data. But the data we're taking so far is showing very clearly that current is going through all these paths in big numbers.
So, Joe, this is David with NVIDIA. I've got some engineers doing the same measurements. I am seeing, I'll say, similar ratios to you. We're using real hardware, not E-loads. So I've got an AC content depending on, what software firmware programs and settings we have. So I'm somewhere between 25 and 30%, as far as what's going through the difference going through the steel. But I'm not seeing it additive through the server chassis that are closest to the power shelf. They're all staying relatively the same. And I just got this data this morning, and I don't understand, why it's different than what your hypothesis is. So I wanted to let you know, we're seeing similar but not the same.
Yeah, and I don't have enough. So we're early here in our ORV3 journey, but I don't have enough shelves, I don't have enough loads, and we're trying to acquire the hardware we need to collect better data. But when you say you're seeing 30%, 25 to 30% flowing in the steel,
yep.
Well, how does it get back?
I'm assuming. Well, that's what we're trying to figure out yet. It's pretty difficult to instrument up our systems without introducing, additional impedances. So we've got compute and switch trays. So I kind of instrument a tray, but I have to remove the tray on top of it to fit the probes.
Yep.
So we're, close. And like I said, I just wanted to share with you that we're kind of mimicking your numbers, just they're not adding like we kind of thought they would. So I'm trying to figure out what the paths are. We're trying to isolate metal, doing just a series of experiments to see what the differences are.
Okay. So this came up, in my design organization because we were just trying to decide up front whether we were going to use isolated or non-isolated DC to DC conversion coming right off the bus bar. And, that's why we kind of investigated this. It's like, well, if we go non-isolated and it's just really the unified ground, then current's going in all over the place. And so we need to think about that. One of the things that we're looking at is if we just use isolated conversion in each ITE, then all the current goes back on the return bus bar. There's no current flowing in the chassis or the chassis ground bus bars on the bus bar assembly, and it feels nice in that way. It's just that I remember as I was at the show at the summit recently, going around talking to people. And people were like, that ORV3 is deploying in volume, right? Like you're obviously a little late to the party to bring up something like this. And I get it, but I still have to answer the question for our organization, like where's the current going, and is it a problem or is it not? And especially as we go up to these really high power racks, that's the thing where there could be current going in places that we don't expect. And if it's a 15 kilowatt rack, maybe who cares, right? It's not a big deal. But I'm concerned that I'm very concerned that as we try to go up to high power, we're gonna find, pieces of glowing metal in places we didn't expect. Anyway, so that was my topic, and we're still collecting data. I can come back and share more data as we get it, but to me, this is something I think that really needs attention and analysis.
Joseph, this is Mike Wingard with Amphenol. One other interesting point that you might want to include is the ground path in the vertical bus bar, at least in our bus bars, is actually aluminum, not copper.
Yep.
Matte tin over nickel, aluminum.
Yep, I thought about that, right? The aluminum is about half the conductivity of copper, but there's two of them.
Yes.
And
they're big.
And they're big. They're big and thick, right? So we're doing different experiments, for example, to isolate these paths, right? So, for example, we did an experiment today to try and isolate this connection and just see how much goes through the steel versus the return. And similarly, I mean, it's if we can either bond this wire or not bond it, and see what that does. But we're trying to understand the different paths. Let's see. So anyway, so that's this one topic. We're going to continue to do more work on it. David Moore and myself have been exchanging email to just try and see if we can come to some kind of common understanding. There's another question that I wanted to ask people about that's completely unrelated to this, but it is related to the bus bar. And that is, at Oracle, we had another architecture of, servers and racks that involved bus bars. And we were using a matte tin over nickel plating on a copper bus bar with a connector not very dissimilar from what what the ORV3 one is. And we ran into a pretty significant problem of fretting corrosion on the matte tin due to micromotion of the the mated surfaces, just from shipping and even from just systems sitting in the data center. And it's something that we came up with a treatment for that was effective, but it was a pretty painful experience. And so coming into this Core V3 and reading and learning all the different details. And when I saw that the chassis ground bus bar is at tin over nickel, I was like, gee whiz, has nobody in an OCP run into this problem before? And I went back to IEEE and just searched on fretting corrosion problems on bus bars plated with matte tin, and it was like 10 or 20 papers right there for me to download to read all about it. Is that a topic that's been discussed here at all? Is it something that people think that they understand and know how to deal with?
Joseph, it's Harry. Explicitly, no, I don't think so, but it doesn't stop us from adding this as a topic where, first of all, I think this is the work you have done. I think it's excellent. And you're working with David. I think it brings a lot of experience and, a problem which I believe we haven't seen, and could potentially become an issue. And I think we can set some, good practices based on this, right? So, no, so to answer your question, no, it hasn't, but, we can set it up and we can, I'll reach out to you on the side and, we can set it up as a thing and discussion topic. I mean, it's all community thing and, whatever you want to bring to the table, it's really good.
Okay.
Yeah. One other point that may help as well, Joseph, to give you some context in I'm aware of the testing that was completed on both of the racks for the OCP base spec, and they went through the standardized ASTM standard of shipping tests, both impacts and shock and vibration testing. And we didn't see any failures related to what you mentioned that you've experienced in the past.
We didn't see any failures either. It wasn't until the equipment had been installed for 6 months and then we started having servers dropping out because the bus bar corroded to the point due to fretting corrosion where we weren't getting good power anymore. I know that on this bus bar assembly, the 48 volt and 48 volt return bus bars are silver plating, and so I'm not an expert on all the different combinations of contact metallurgy, but I don't think that that's subject to the fretting corrosion problem that matte tin in particular is.
Yeah, we also I'm a little bit aware of obviously the V2. We had threaded power into silver plated bus bars, and that we had no issues there that I'm aware of for the lifetime of that product for kind of 10 to 7 years. So and most of what was kind of defined for the V2 bus bar, obviously different voltages, but in terms of the plating and other requirements have kind of been used again in terms of confidence because of how it performed previously.
That was the silver plating for the main bus bars.
Right? Oh yeah, sorry, you're talking specifically the aluminium. Sorry, is that right?
Yeah, right. The chassis ground bus bars are aluminum with nickel, and then matte tin. So it's really that one that I'm concerned about, and it's an interesting one because would you expect to see any failure with that got badly corroded? Probably not.
Mike, have you got an answer, or from your experience, this is something that Amphenol have recently added?
Yeah,
I mean, adding the tin plate versus the silver plate is a very important problem because I have experience with the original V2 Facebook failures that occurred on many racks at TE, and very concerned about having tin plated bus bars for the server, even though we bumped up the voltage from the original V2 to the V3 to 4850 volts. That's something we need to be very concerned about. Even though they may have passed the shipping test, the Facebook failures in these racks was significant. And this was 5 or 10 years ago, the original V2 racks.
Sorry, they used matte tin for the power bus bars in that experiment?
Joseph, will you speak louder and into your mic? You're
very garbled to me.
Oh, I'm sorry. The thing you were just talking about, was that with the failures at Facebook, was that a matte tin finish on the power bus bars?
think it was nickel only. The original OCP spec was.
Nickel has the same fretting corrosion issues that tin will.
Mm-hmm.
I think we're mixing up topics here. So I think, sorry, I started that. What I think he's asking about is, Joseph's asking about is the grounding, so the aluminium extrusions. Is that right? Nothing to do with the power, yeah.
Correct. That's the only one that I've seen in the literature that describes having a matte tin over nickel, and that's exactly
and that's correct for me. That's right. So the power for V3 is a silver-plated buzz bar. So Mike Wingard, can you answer on the aluminium element? Have you experienced issues with that in the past on your other products or anything?
We have not. However, I just want to make a comment that the ground path through the vertical bus bar, at least my understanding was it was a secondary backup to the primary chassis ground through the rack itself. So this not being a primary device, we did not feel that it was a significant concern, but it's something that we can definitely look at. And unfortunately, I mean, to go to silver, which is easy, will be more costly as well. So that's partly why we used aluminum and tin, is to help keep weight and cost a little bit more manageable.
Yes, the secondary sense contact with that tin plate is really just that, a sense contact. And you're right, the original Facebook bus bars were plated with bright tin or bright nickel, which was horrible.
Right.
And that's why the jump to silver was so important.
Hey, this is Bobby Pizzo from Molex. Just a quick comment to pile on to what Mike said. Is the spec for the ground contacts in the ORV3 spec is actually only a 2-minute surge at the 64 amps. So I think some of the discussions early on in that development were around it being that short duration kind of fault current, not a steady state, it's going to carry current for the next 10 years situation, right? And so that part of what drove the tin plating, as Mike suggested. And just another comment as far as testing for fretting. I mean, I think the shipping test and normal EIA shock and vibration tests are great, but there are fretting tests. I mean, there's a thermal cycling test that's typically done. It's a much longer duration test to kind of, you know, estimate the micro motion that could be seen over the life of a product. That's a much harsher, you know, fretting test that is done on many tin plated products. That's something you could look at, but it was not part of the spec and not something that, at least from the Molex side, we did not test that from a connector qualification standpoint on the ground contacts.
Did that help answer some of your questions, Joseph?
Yeah, I mean, it sounds like the number of people here have experience with fretting corrosion with tin and apparently with nickel as well. It doesn't seem as though there's much evidence to suggest that that's not going to happen here on the ground bus bars. It just, I don't know, it seems like people are aware of it, and but nobody's very worried about it. I don't know, does that sound like a good summary?
I think it's an excellent point, and you know, exactly.
Yeah, I think, Joseph, I think you obviously got a special, you know, piece of, mainly on the grounding element of it, you know, insight in something that maybe others haven't considered. So maybe like a detailed, I don't know, maybe not a white paper, but maybe a detailed presentation of something that we can extrapolate eventually into some sort of guideline that we can discuss with the community and see if it's the right way to go. That would probably, we could adventure further on it if you wanted to.
Yeah, well, I mean, my guess is probably a lot of you are in the same situation I find myself in, which is the most important thing is to make sure that you don't have the same bugs on this product as you had on the previous product.
Mm-hmm.
And so for me, matte tan over nickel is like a live wire that I don't want to touch, and politically. And so my inclination is to not do that for whatever we end up making. And maybe we do silver on those bus bars as well, and we just pay for it. But we went through a lot of pain on fretting corrosion, let me tell you, and nobody here wants to go through that again. And so as we understand the current flow in the rack better, I think that may amplify or reduce the concern, but it would be curious to ship the rack with a plating that you expect to fail. And based on my past experience, I expect it to fail. I expect that there's going to be fretting corrosion, and the resistance of those ground contacts is going to go very high over time. On not all the racks, but 20% of the racks, maybe over the course of a year or two, you're going to find out that you have poor connection to the chassis bus bar. That was my experience. And so, internally here, I'm going to act on that. And, like I said, there's lots of material out there on the web about fretting corrosion on matte tin. So.
And Joseph, quick question on that. As far as you're talking about running more of a steady state, potentially higher current through those ground contacts over the life of the product, correct? Not a short 2-minute burst in a fault current. Is that correct?
What I stated earlier is that the meta approach of a common grounding strategy in the rack, I believe, is going to have steady state current on the ground contacts, but the magnitude of it is not clear to me yet. It really depends on whether the currents are additive as you move up and down through the rack. And I don't know that yet. We're still doing experiments. If they are additive, which my original thinking on it made me expect that they would be, then yes, there could be some, a lot of current flow in there. But it's a strange situation because fretting corrosion in that case would make that contact really poor, which would actually reduce the current flowing in the bar clip grounds, which is a good thing. You know what I mean? It's like it's a curious situation where I'm expecting fretting in a place where I really, if we were doing a unified ground, which I'm not really inclined to do, but if we were to do that, then having a much higher resistance on the ground contacts on the bar clip connector is advantageous. It's just not good for safety, right? I mean, if what you're trying to do is have, like, if I went to a different design and used isolated converters into each of my servers, and then I don't have any current in the steel, I don't have any current in the ground bus bars, and the only thing there would be fault current. Well, the reason those contacts are there is to protect human beings. And so you don't really want high resistance contacts due to fretting in the safety case. So it's a multifaceted, strange problem.
Hey Joseph, this is Laurentio Lari here from Microsoft. I wanted to add a couple of comments on your conversation on ground currents. So my expectation is that the power source, like in this case, power shelf, it would have an ground connection. Has to pass safety. So
well, it has. Sorry, go ahead.
Oh, I'm not familiar with the implementation that OCP has. I kind of joined recently's effort for Microsoft, but the expectation is it has that ground connection. So I'm curious how you block that chassis connection.
It definitely has a ground connection, right? So here's my picture of it. This is the power shelf, and the whip brings in the earth protective safety ground, and that's bonded to chassis. But the return bus bar is not bonded to the chassis as well. So there is a protective ground, and by virtue of the chassis, you know, this is touching the rack, so the rack is connected, and this chassis is directly mating to the bar tip of the ground contact up here. So, you know, the bus bars going up the back are definitely connected to the safety ground. So
Okay.
I don't think there's an issue there. It's just that, you know, for an individual chassis, if I was worried about a fault current, I don't know what that means.
But each chassis is connected in by the rack between each other, right? Every chassis is pretty much bolted to the rack.
Yeah. So there's no question that each chassis is connected to what I call chassis ground, the protective earth, right?
Right. So there is definitely a super connection between all of them.
Well, the chassis is sitting on the shelves. For ORV3, you know, the option 1 ORV3, it's just gravity holding it in place, really. It's not bolted or. Yeah, so from a safety perspective, you could say, well, the power shelf is connected to earth, and the degree to which the power shelf is connected well to the rack, the whole rack is covered regardless of what happens on the bar clip connectors. Is that your point?
Yeah, the other question I have is a bar clip connector that provides earth ground connections to the bus bar earth ground rail. That's pretty solid connection for all of them, for all of the servers, including the power shelf, correct?
I didn't understand the question. I'm sorry.
So you have a good contact for every earth ground connection at server level and power shelf level, correct?
Yeah, the bar clip connector normally makes an excellent contact, right? It's just we were talking about fretting corrosion, and that would affect this one because the pink resistors here represent the aluminum bus bar, which is matte tin over nickel.
No. What I mean is if you scroll down on the power shelf,
Yeah.
the power shelf earth ground contact that you show is directly connected into the power shelf, but not to the chassis, you say. But
no, the earth ground is connected to the power shelf, and through the bus bar on the back, every chassis connects to it.
No, so that location, the bottom location, the bar clip return connection, that it should be the earth ground connection. That's the
earth ground. And that's the part.
That one. Okay, so that one's connected to chassis, correct?
Yeah, it's bonded to the chassis right here.
All right. So I'm not sure, and I understand why you think it's not returning through the power shelf if that chassis is connected there.
Return current. This can get to the power shelf. It can't get into the power supplies because the power supplies, right? This represents the 48 volt bus bar going up the rack, right? 50 volt, I said, right? And this is the return bus bar coming back to the power supplies. And so all I'm saying is any return current in the rack that's flowing in the steel or flowing in the ground bus bar, it can't get to the power supply through the power shelf. The power shelf and the power supplies only connect to the return bus bar. And so, but there are current paths elsewhere where current can be flowing in these other places. The steel is shown in blue, the chassis bus bar is shown in pink or red. That can come through this server, through its steel, and get back onto the return bus bar that way. And so it's those kind of parasitic paths are the ones that I'm concerned about in terms of their current handling capability. And it doesn't seem as though this has really been, analyzed or
okay.
considered carefully. So
the other question I have is related to the expected value of the earth ground current. If when you look at these AC systems, three-phase systems, and the expectation is that you could have up to a 30% phase imbalance. That's what you get. That's how you get your earth ground return. So I would say that's probably one one target maybe you could expect.
That's the neutral line, though. That wouldn't be the earth ground.
You could have also phase imbalance between down to between the normal phases, like where you should be, all three phases versus the ground. So you could also have voltage.
Okay.
Residual voltage. You could also have residual voltage differences between the points. So then, but the expectation is that the phase imbalance will give you more of this return current.
Yeah, you've lost me with your discussion of phase imbalance. I apologize. I understand three-phase power fairly well, but I'm not understanding the point you're trying to make.
So the point I want to say is if you look at the literature about how much earth ground protection you should target.
Yeah.
There is like a 30% target, and this is actually, if you look at the connector ratings, like the Barclay contacts, the earth ground contact is like around 30% of the standard positive and return ratings.
Yeah,
So just want to bring you up to that.
Yeah,
There might
that's
be
another loop on the source side. So you're neutral and ground, in a Y-based system. What he's talking about is the potential difference between neutral and ground, which are tied back together at your transformer, the ground bar right at the transformer. I forget what the spec is there. I think it's either 3 to 5 volts worth of potential difference on neutral and ground, and that's what imposes a limit on that current.
Yeah, if you just consider a residual voltage. Yeah, and there is the effect of the phase imbalance too.
Yep.
But so I mean, it looks like the industry is kind of targeting a 30% expectation of current rating for those contacts. Like the bar clip connector is that way.
Yeah, and that's I was trying to visualize the actual fault that was being anticipated here, and I haven't really figured it out. But the only thing I could discern was, well, if I have a 30 amp whip, then each of my 3 phase of my Y whip is breakered at 30 amps. Is that where the 64 amps comes from, which is twice that for 2 minutes? I don't know. Like, what is the fault that's anticipated? I mean, we don't have to talk about this, but this is a question that I had.
I was curious if anyone considers phase imbalance to be actually the real problem, and if that were the test.
Yeah. Anyway, I think I've used up enough of your time. Unless there are more questions.
Yeah, I appreciate it. Thank you.
Thank you. It's been an excellent discussion. And as a next step, as Stephen suggested, Joseph, it's possible that we can, put these things together and as a white paper or some sort of guidelines, and that would really help. And then we can use this for the community to comment and add to it, right? If that works.
Yeah. Well, the thing that I'm hoping we can get to is an understanding of where return current flows in these alternate paths. If we continue to pursue, or everybody can do their own thing, but in a unified grounding design, to understand where the currents go, whether they're additive or not, and that is going to probably put some limitations on how high you can take an ORV3 rack in terms of power. And so when we figure that out, then it'd be like, okay, the ORV3 rack as currently described in the literature may only take us up to 25 or 30 kilowatts. That's what we don't know yet. But I expect that there might be a limit like that before some of these paths could become problematic, or maybe we have to have, like, depending on your power in the rack, the bonding wire in each server has to be, rated for a certain amount of current and temperature rise and so on and so forth, which is kind of an interesting thing because, that means the internal design of an individual server depends on the aggregate power consumption of the rack, which would be kind of an unfortunate situation if that were to arise. So it's those kind of things that we need to understand.
Okay, I think that's some good discussions. I think, like we said, Joseph, if you wanted to in the future pull together something in a bit more detailed and maybe turn into some sort of white paper or spec, that would be good, and we can look into that. But for the minute, is there any other topics anybody wanted to raise? Or
hey, Stephen, I just wanted to say real quick, there was a mention about the 33 kilowatt power shelf earlier in the call. And kind of some of the challenges with it, it's just with the, the one rack U height and needing the cable to come out parallel to the power shelf and then take a 90-degree bend. So I have some ideas with that. Harry, we talked about it a little bit at OCP Summit, and I'd be happy to present those on a rack and power call. But Harry, I think I'm going to reach out to you. I just want to get some discussion with you beforehand, just to make sure that our ideas are relevant. But yeah, I just wanted to make that comment.
yeah, that's absolutely fine. And like you said, Harry can decide whether it is on the power side. But yeah, that's no problem at all.
Cool. Thank you.
No, good point, Bill. Let's just work and we can schedule that for the next call. Thank you.
Perfect. Thanks.
Okay. All right. Well, thanks for a good call, guys. Speak to you later.
Thanks, everyone.
Thank you.